this is Captain Chaudhari. In my series of videos on basic stability calculations, today I'm going to do the importance of the use of moment of inertia of waterplane area in finding out what is the BM of what is the stability of the craft. Basically, BM is equal to I upon V. That is the vertical distance between the center of buoyancy and metacenter is equal to I upon V, that is moment of inertia of waterplane area divided by underwater volume. So if we are talking about BM transverse, then the axis is fore and aft axis, right, passing through the center of flotation. So I had done the application to find out the center of pressure, but now today we will start the use of moment of inertia in finding out the BM. Now in this video I'm going to talk about the importance of the waterplane area, right? So BM, the vertical distance, is equal to I upon V, I had said earlier. So in this video I'm going to talk about the importance of the moment of inertia and underwater volume in finding out the vertical distance BM. BM is equal to I upon V. Suppose we talk about a craft with a rectangular waterplane, and if the axis is passing through the center of flotation and is a fore and aft axis, then moment of inertia about this axis divided by underwater volume is equal to the BM transverse. So for a rectangular vessel, the certain dimensions, they get cancelled. So what we have finally is BM transverse is equal to B square upon 12D. Similarly, if we talk about BM longitudinal, it is L square upon 12D. So what I mean is the transverse stability for a rectangular vessel really is not dependent on the length, except that it influences the underwater volume. But if you see in the formula, there is a great importance, there is a higher importance of the breadth of the vessel, right? So we must know that if a vessel generally is more broad, it will be more stiff, its stability will be better, right? So let's do a simple case of finding out the BM transverse or the stability of a floating drydock. A simple question about the floating drydock. Now this floating drydock, this question is from my book, that is the Basic Stability Calculations, Basic Ship Stability. It's a floating drydock of a double bottom, which has got a double bottom of depth 6 meters, right? So here is a double bottom. This is 44 by 44 meters by 6 meters, and above this double bottom we have side tanks which are of the width 4 meters, right? So draft of the floating drydock is 8 meters, and we need to find out what is the GM of the floating drydock. It is given that the kg is 4 meters. Okay, now the first thing that we should be doing in such a calculation is look at the transverse profile of the craft. Now looks like the transverse area is same all over the length. That means in case we take any of this transverse section anywhere along the ship's length, right, we see a transverse profile, and if we look at this transverse profile, the area, if we find out the centroid of this area with respect to the base, with respect to the keel, that distance will also be the kb of the craft. So instead of involving the full length of the vessel, let us find out the centroid of this transverse area, right, by taking the moment about the keel. So first the moment of the double bottom, that is 44 into 6, this is the area, multiplied by the distance 3 meters, because the centroid would be 3 meters from the base. Now we take the tanks, that is the side tanks, separately, right? So there are 2 tanks, and the area of these tanks are 4 into 2, 2 into 4 into 2, right? So that is the total area of this tank, and the distance from the centroid of the tank till the base, you can see, is 7 meters, right? So this is the moment of the area about the keel, and total area would be 44 into 6, right? 44 into 6 plus 2 into 4 into 2. This is the total area. So let's find out what is the kb of the floating drydock. 44 into 6 into 3 gives me 792 plus 112, right? Divided by 44 into 6 gives me 264 plus 16. So that is equal to 4904 280. So 904 divided by 280 gives me 3.22, let's say 3.229 meters. That is the kb of the craft, right? This is done by taking the moment of area about the keel. Now next we need to find out what is the moment of inertia. Now moment of inertia of the waterplane area, if we cut the floating drydock along the waterline, we will just find this area and this area contributing to the waterplane area. And actually, if you talk about the center line of the craft that is passing in between the two vertical tanks and is in over here, right in the water, this is the centralized center line of the craft. Now moment of inertia of these tanks, right, which may be of the length L, and this distance is 4 meters about the own axis passing through the centroid, is given by L into 4 cube upon 12, right? Similarly, we'll have moment of inertia from this side. The moment of inertia about the own axis is L into 4 cube divided by 12. Now if I want to know what is the moment of inertia about the common center line, so it will be like this is 64 L upon 12, right, plus AD square. What is the area of this tank? That is 4L. What is the distance, like half of 44 meter, which is the total breadth, is 22, and this distance from the centroid axis to the common axis, this distance will be 2 meters less. So half of 44 is 22, 2 meters less is 20. So D is 20. If I want to transfer the moment of inertia from here to here, D is equal to 20. So AD square means 20 square. Now this moment of inertia is coming from the other side also, so I multiply it by 2. So this is the total moment of inertia by given by these waterplane areas, which are provided by the side tanks about the common center line of the ship, of the drydock, right? Once again, moment of inertia about the own axis is 64L upon 12 plus area, that is 4L, into D square. D square is 20 square. Now this is the total moment of inertia. And what is the total underwater volume? Total underwater volume, look at the waterplane area. What is the waterplane area? Now waterplane area is given by 280 meters is the waterplane area, and 280 multiplied by L is the underwater volume. Now let us see what happens. The L gets cancelled, right? So L would get cancelled. L, I can take common and then cancel, but L gets cancelled, which means that in deciding the transverse stability of this craft, L is really not important. So whether the drydock is 10 meters long or 20 meters long or 200 meters long, the transverse stability would be same, right? So let us see how much you get. 64 divided by 12 gives me 5.333. 5.333, right? And then 400 into 4 is 1600 divided by 280. Okay, then this whole thing is multiplied by 2. So I have 5.333 plus 1600 equals into 2 equals divided by 280 gives me 11.467. 11.467 meters is the BM, that is I upon V. So 11.467 plus KB. KB we have got is 3.229. So I have KM is equal to KB plus BM, that is 11.467 plus 3.229. That gives me 14.695. 14.695. And I have kg, which is equal to 4 meters. That means the GM of the Drydock is 10.695 meters. On the same lines, we can do the stability calculation of a catamaran. The principle of catamaran. Twin hulls. We have twin hulls which provide higher stability, and that's what we are going to see. Like if you have a pontoon of this size, something like this, and if you join this pontoon with another pontoon of identical, and just for the ease of calculation, let us assume that the platform that is loaded on top is weightless platform. So let us do a question once again from my book. So there is a box 4 meter broad, draft is 3 meters, right, and has a kg of 2.4. kg is 2.4 meters. It's required to find out GM transverse, right, after it is connected with an identical box with a weightless platform on top, such a way that the boxes are 6 meters apart as measured from center line to center line. Center line to center line, they are 6 meters apart. The draft is 3 meters and kg is 2.4 meters. The principle of catamaran is similar to the principle of floating Drydock. Let us do this question, right? So in this particular case, what's happening is the platform on top is weightless, which means that after joining the platform, the kg of the crafts is not going to change. Now, if we want to know what is the stability of the single pontoon before joining, that is, kb was half of the draft, that is 1.5, and bm is equal to b square upon 12d, and that is 16 upon 12 into 3, because draft is 3 meters. So 16 upon 36, 16 divided by 36 gives me 0.444. So 1.944 is the km, and if the kg is 2.4, you can see that the GM is negative. So there is a negative GM if we talk about the single pontoon. Let us see, by joining these two pontoons or using the catamaran principle, GM becomes positive. Let us look at it. Now, since the platform is weightless, we would say that the combinations KB is also same. The catamaran, the combination, the KB is going to be same, 1.5 meters. kg is also going to be same, 2.4 meters. But then what happens? Let us look at the plan view, same like last question, right? What is the moment of inertia about own axis? Moment of inertia about the own axis will be L into 4 cube upon 12. Now center line to center line distance is 6 meters. So center line to common center line, the distance would be 3 meters. So the moment of inertia as it is transferred from own centroid to the common center line will be AD square, that is 4L, that is the area, into 3 square, right? But this moment of inertia has to be considered from both the sides, from here as well as here. The total moment of inertia divided by the underwater volume. And underwater volume, look at the graph, 3 meters and breadth 4 meters, 12. Over here 12, over here 24 is the area. So multiplied by length, 24L is the underwater volume. So L gets cancelled like last question. L gets cancelled. This is 64 divided by 12 plus 36. Okay, the whole thing multiplied by 2 divided by 24. This is going to be the BM. So 64 divided by 12 equals plus 36 equals into 2 equals divided by 24. Gives me 3.444. 3.444. This is the BM transverse. So KB is 1.5, BM transverse is 3.444 meters, which means that the KM would be 3.444 plus 1.5, that is 4.944, minus kg, that is 2.544 meters is the GM of the combination. So you've seen that the single hull, that means the single pontoon, had a negative GM which became positive when we use the same box, same pontoon in combination to make catamaran. So this is the principle of catamaran.